Hi there. Hey, let's do some sample problems to get ready for the Chem 26 General Chemistry 2 exam. Let's see, I think it's Unit 4. So I'm going to pick a few questions off of the sample test. So make sure you take a look at all the sample test problems. Some of them are repetitive to give you more practice, but others highlight some important details that could show up on the exam. So I'm going to go over what I think are the most difficult ones. I was about to say most important ones. I'm actually leaving out a couple of the important ones that are fairly straightforward. So if you have trouble, post a question in the discussion session, discussion posts, discussion boards, that's what they're called, and see if your classmates can help you out, or send me an email. And let's tackle what I think are some of the more difficult ones. Oh, but first, let's take a quick overview of the sample test, which will look very similar to the actual exam. So here we got, sorry, setting up the pen. There we go. At the top here, we got some equations and data. So these are the equations that you will get. You don't have to memorize them. Right down here is Electrochemical Series. It has all the ligands from strong field down the weak field. And it's right here between ammonia and water that you need to know. It's kind of the cutoff, right? So ammonia and more to the left are the strong field ligands. Water and those to the right are the weak field ligands. We'll get into strong field and strong field and weak field ligands in a few minutes. Also, there will be some nomenclature, meaning you'll have to name some transition metal complexes. I'm not expecting you to have all these ligands memorized. So they're here for you, as well as their names. So their names are appearing in the same order. Just be careful, and you should be able to line things up. I know you can get easy to get lost in the middle here, but water is right here, and here's aqua. Sounds like agua, Spanish for water. And then C2O4 2-. Hopefully you do. One of the polyatomic ions is oxalate, so oxalato. Hydroxide, hydroxide, serious hydroxyl. Okay, and fluorochlorobromine. Yeah, okay. So you'll be able to find your way through the names. And then over here is the standard reduction potentials. It's a long list. I posted the whole thing on the sample test. I think I will probably shorten this up and only, I will make sure that the ones you need will be on this chart, but I'm not thinking about putting the whole chart in there because it's a whole page long. It's going to take a lot of room. So I'll shorten it up and just include some of them and I'll make sure that the ones you need are in the list. Okay, let's take a look at some of these. So first one here I chose was balance this chemical equation in an acidic solution. Sorry for the typo. This is balancing a redox reaction. And it takes more steps than just making sure the coefficients are correct. So if you have an oxidation reduction reaction, you should split it up into half reactions. That's my first step. So I got zinc here, and it's going to turn into zinc 2+. That's one of the half reactions. So I took care of this thing and that thing. The other half is AS2O3 going to ASH3. Okay, so there's the other half reaction. So step one done, split the unbalanced equation into two half reactions. Second thing, make sure that you have the same number of redox active, the metal or the atom, and not necessarily metal. It could be non-metals too. The element whose oxidation number is changing, make sure you have the same numbers. That's the first thing to do. Make sure your redox active metal with the oxidation, the atom with the oxidation number that changes, make sure you have the same number. So yes, there's one zinc on both sides, but here, AS is arsenic, I believe. I misplaced my periodic table. AS, there's two of them on the left, but only one on the right. So put 2 here, now it's balanced on with respect to AS. Third thing is get your electrons in here. So what's happening when zinc, a neutral metal with no charge, changes into a zinc ion with a +2? Well, the metal had to get rid of 2 electrons. And then if you want to check your charges, yeah, +2 and a -2 gives you a 0. Yeah, that charge is 0. That helps. Okay, the metals are nice because you can use their charge to get to the oxidation number pretty quickly. Here I got no charges. These are covalent compounds. So we need oxidation numbers. Okay, so when we have a covalent compound, I really do miss my periodic table. AS, oh, I put one in here. Gotta have a periodic table. There it is. So you'll have a periodic table on your exam too. AS is arsenic. Ooh, and it's above the staircase, so it is a non-metal. So I need that because arsenic with oxygen means 2 nonmetals are attached together, making a covalent compound. And then arsenic and hydrogen, well, you remember hydrogen's kind of exception. It is a nonmetal, but not found on the right-hand side. It's in the top left. There it is, there's hydrogen, but it's a nonmetal, even though it's found among the metals. Okay, covalent compound. So when you're assigning oxidation numbers and you have a covalent compound, you then see if you have a fluorine or a halide. Typically you assign that a -1. An oxygen, ooh, we do. The oxygen we assign a -2, and there's 3 of them. And hydrogen we assign a +1. We'll do that next. But this arsenic atom, we have no idea what its oxidation number is. So I'm gonna call it X. And in this compound, there's 2 arsenics. And the idea is if you add up all the oxidation numbers, they have to equal the total charge of the complex or compound. And there's no charge up here, so it's 0 is the net charge. So 2x - 6 equals 0. Add 6 to both sides. Divide by 2. So arsenic starts on a +3. Each arsenic is a +3. And then what's the arsenic afterwards? I'm going to omit that 2 and just look at one compound. So one arsenic compound, so the oxidation number of just one arsenic atom, plus there's 3 hydrogens, and this is a covalent compound, so assign hydrogen a +1 charge or oxidation number. And then all these oxidation numbers have to total to 0. No charge on that molecule. So X + 3 equals 0. Subtract 3 on both sides. Arsenic went from a +3 down to -6. It was high, then low. It just got reduced. I don't know why I'm going over that. It just jumped in my head. The metal, maybe when we have to look at the electrochemical cell, we need to identify who's being oxidized, who's being reduced. So this is helpful. Zinc started with 0 oxidation number. It went up to +2. It just got oxidized. And oxidation, oil rig, oil oxidation is loss of electrons. Hey, zinc, you're missing electrons when you move from the left to the right side. Yeah, zinc got oxidized. It lost some electrons. How many electrons did arsenic gain, right? It went from 3 down to -. It was reduced in value. Well, it needed 3 to get 3 electrons need to be acquired to get to 0, and then it needs another 3 electrons to get all the way down to -6. So each arsenic needs 6 electrons, right? And you could say, okay, well, a +3 - 6 equals a -3. But that's per arsenic. So there's 12, yikes, that's a lot. 12 electrons are needed so that both arsenics can get 6 electrons, and its oxidation number can go from, what is it, +3 for each arsenic, down to a -3. Okay, so that's my half reaction so far. Balancing like the oxidation number, adding in electrons. Next, balance the charge. Zinc, you're so easy. On the left side, there's a net 0 charge. On the right side, 2 - 2. is 0. Net charge is 0. Charge is balanced. Going down here, this molecule is neutral. This is a minus 12. On the right side, there's no charge. Okay, it's not balanced. Okay, so we need to know what the pH is. If it's basic, you get to add hydroxide ions, right? So a basic solution means there's an excess of hydroxide ions. So use them in your redox reaction. If it's acidic, well, then you know I have an excess. You have to add H pluses. And so that's why this detail and acidic solution was given. So now we know add some H pluses to balance the charges. Well, what we can do with those pluses is add them over here so that we can cancel out the charge on the electrons. There we go. So now the net charge on the left side is equal to 0, which balances the net charge on the right side. Cool. What's next? We just added these hydrogens, so balance those. No hydrogens here. Yay. Zinc, you're already balanced with respect to hydrogen. Good. Well, we got 12 H's here. We got 6 over here. So we need 6 more. But you can't add H pluses because that'll mess up the charge. So you have to add water. So I need to add water so the total number of hydrogens is balanced. I got 12 here. Come in with 6 on the right. I need another 6. So that means 3 water molecules are needed. Give me 6, or rather a total of 12 H's. Yep. And then now I just added a water molecule, so I need to balance the oxygens. Well, hopefully it's already balanced. If it's not at this point, it means we messed up somewhere. We have to go back and just find our error. But thankfully, there's 3 oxygens on the right, and there are 3 oxygens on the left. Okay, our half reactions are now balanced, but the goal was to balance the whole darn thing. So now we need to merge these half reactions back together so that the electrons cancel out. There's not going to be any electrons in the overall reaction. It's a redox reaction. Someone gets oxidized, someone gets reduced. They swap electrons. There's none left over. So they all kind of cancel out. So let's get these electrons to cancel out. Zinc's producing 2 electrons, but arsenic needs 12. Okay, so how do we take this up to 12? Multiply the whole thing by 6. So now the half reaction is 6 zinc metals go to 6 zinc ions, and that will produce 6 times 2 is 12 electrons. Okay, now add this half reaction to this one. And so what I like to do is just list all the products together. So starting with, give me some more space, please. There we go. Okay, so starting with the zinc, the products over here are 6 zincs, and we might as well get the physical states in here now. That's zinc metal. And then that's all the reagents for this half reaction. For this reaction, half reaction, we have the arsenic oxide, and the electrons are going to cancel out, so I'll just leave them out. And then we have the hydrogen still. Oh, physical states. Are we told what arsenic oxide is? I think it should be. Or not. Let's use our solubility rules. That should be a solid. Oxide. Oh, yeah, it's a covalent compound. What am I talking about? Can't use solubility. Make a guess. I'm not going to take off points for that. You should know that zinc metal doesn't dissolve in water. But this one, actually, we don't have any information on. So I need to provide that. Or in this case, if it showed up on the real exam, I would just leave it out. What did I put on the, on the answer key, I didn't put in physical states. Go figure. I still would like to see them. So anyways, do the best you can. Sorry, that sounds terrible. All right, so let's be a little more to the point. Zinc metal, you should know. H plus, you should know. If you see something, I attempted to use solubility rules on it, but this is not ionic, so it doesn't work. I will do a better job on the test. What I should have done is in the question, for the one I don't think students would know, I should give you the physical state. And I'm doing it now because I'm going to guess that arsenic hydride, yeah, should also be a solid. But zinc ion, you should know that that's aqueous. Okay, we're still adding our net reaction together. We got on the product side, did I finish all the reagents? Yes. Got distracted with the physical states. All right, for the zinc, the products are 6 zinc cations, aqueous. Electrons got canceled out. On the product side of the arsenic reaction, there's 2 arsenic hydrides, and they'll tell you that it's solid. I'm pretty sure, I'm not positive. Something I have to look up. And then there's 3 water molecules. You should know the physical state of water. When it's in water, it's a liquid. And then check and see if anything cancels out. Like sometimes you might find some H pluses here, and I have H pluses over here, so you can cancel those out. But no, everything looks good. We're done. I think. What was the question? Balance it. Yes, it is now balanced. Cool. And the number 2 gives you question 2 on the sample test will be another problem asking for a redox reaction to be balanced in a basic solution. The only difference is add hydroxide ions. You'll still add water to balance out the hydrogens and the oxygen. Okay, next one. Ooh, this is an important one. And it's not a hard one, but it's important. Which metal, aluminum or nickel, could reduce zinc +2, the zinc S solid, if placed in a zinc cation solution, aqueous zinc cation solution? Okay, the key word here is reduce. So you should know that on that standard reduction potential chart, the one that's given to you with the long list, a page long, that if you look on the right side, you get stronger oxidizing agents. Something you should just know. And if you go on the right side, the product side of the chart, as you go down, you go to stronger reducing agents. And you know what? I'll admit, sometimes on the exam, when I look at this, like, wait, was it stronger reducing and stronger oxidizing? Which way was which? We'll go and look and see what makes sense. So it is this correct way. Oxidizing agents is stronger going up on the reactant side. So if you go up here and you say, oh, F2, what are you getting? You're being reduced. You're gaining electrons. So what kind of agent are you? You're the opposite agent. So F2 is reduced to form F-. And if it's being reduced, F2 is an oxidizing agent. How good of an oxidizing agent? Well, there's a couple ideas. One, how often do we talk about using fluorine gas? Never. Fluorine gas is so reactive. It reacts with the container you put it in. Yeah, so this is a very powerful oxidizing agent, and it oxidizes the container, reacts with the container. That's the first thing. Just know that F2 is so unusual. F- we see all the time, fluoride ion. It's a weak acid, kind of stable. F2 is very reactive. This is a very favorable reaction. It's going to go and eat up electrons, meaning F2 is reduced, and F2 becomes an oxidizing agent. Second idea is remember that spontaneous reactions well, there's a couple of things to remember. One is your delta G should be negative, but we don't have delta G here. We have the standard potential. And so for spontaneous reactions, check and see if the this thing, the potential, electric potential, is positive. And it's the most positive one, which means it's the most spontaneous. It's strong. So this is a scale, like down here at 0.2, it's like, it's just barely above 0. It's a little bit positive. It's definitely spontaneous, but it's not, it doesn't have a lot of oomph, a lot of strength, a lot of drive behind it. But this is the largest voltage. It's the most spontaneous. It's the strongest. It's actually the strongest oxidizing agent on this chart. Okay. And then things are backwards. Hey, fluoride ion, do you like giving away electrons to go and turn into F2? No. Fluoride ion is really stable, somewhat stable. It's a weak acid. So if this is positive, that means as written, it works in that way spontaneously. If you go to the other end of the chart, that's where everything's negative. Okay, so then we just said if it's spontaneous, it should be positive. So this reaction is written, it's not spontaneous. Go up to here to a more familiar reaction like sodium. How often do you see sodium ions? Just grab an electron and turn into sodium metal. That'd be bad, right? Sprinkle some salt in your food and all of a sudden you see a little metallic stuff. Turns into sodium, which likes to ignite when water. No, that doesn't happen. So because it's negative, that's not spontaneous. The reverse reaction is spontaneous, right? So the chain, you have to remember when you reverse this reaction, saying, hey, sodium metal, do you like to turn into sodium ions and kick out an electron? Oh yeah, all the time. Sodium metal is so reactive, like I said, it explodes in water. Cause an explosive reaction in water. So it loves to release electrons. That's spontaneous, not the way it's written. This is as a reduction reaction, but sodium likes to oxidize. So you switch the order, and now the standard potential becomes a positive 2.71. That's a pretty large voltage. That's a very spontaneous reaction as written this way. And what's happening to sodium? We just said it's releasing electrons. It's losing electrons. It's being oxidized. If it's being oxidized, what kind of agent is it? It's a reducing agent. So what I remember is like sodium is a great reducing agent, but these are better. Lithium on this list is the strongest reducing agent. Okay, so it's important to have a feel for the chart, this standard reduction potentials chart. These acronyms, oh, these names of charts and stuff. And the question was, let's look at, I think it was aluminum, nickel, and somebody else. Aluminum or nickel can reduce zinc. So let's go find those. Well, here's aluminum. Here's zinc. And here's nickel. Okay, so the question said, hey, nickel or aluminum, who's best at reducing this thing, helping this get reduced so zinc can grab some electrons and turn into zinc metal? So we want to reduce it. So who's a strong reducing agent? Well, the trend as you go down becomes a stronger reducing agent. So aluminum wins, stronger than nickel. If you totally flub up and get flustered, it's like, I don't remember what Dennis said about this. I have no idea. No, try a different angle. Kind of say, okay, does it make sense that aluminum reacts with zinc? That was a question said. Which one is more likely to do it, aluminum or zinc, and react to reduce it? Okay, so take the aluminum, which they said that was a question. Will aluminum do it or nickel? And then you're going to take this one and you want to flip this reaction. So now the standard potential for aluminum is now a positive 166. And then zinc is reacting as written. So keep the sign the same. We're going to add it to a minus. So this standard potential is, there it is, minus 0.76. And that looks like 0.9, right? Volts. If I do the math in my head, is that a positive or negative number? It's positive. What do we say about voltages being positive? It's spontaneous. So the answer is yes, this will work. Aluminum can react with zinc metal. And then just make sure it doesn't work for nickel, right? So the question said, will nickel react and reduce zinc? Okay, well, nickel is not a reactant. I want it to be a reactant, but right here off the chart, it's a product. So I need to switch it. So the standard potential is going to be a plus 0.25. Zinc is still written in the correct order. I want it to go from zinc plus 2 to zinc metal, and it's a minus 0.76. And then this is 0.51 negative. If you do the math, that's a negative voltage. If it's negative, it's not spontaneous. This is non-spontaneous, which means, nope, it's not going to react like that. Cool. Nice. Let's check and see if I answer the question. Which metal, aluminum or nickel? So we discovered aluminum is a stronger reducing agent. 6. Given a galvanic cell described by, the standard cell notation, sketch it. All right. Okay, what's kind of cool is it's standard. If you're into memorization, it does go alphabetical order. The anode is listed first and it goes to the cathode. If you forget that, then just remember that this is one half reaction and this is the other half reaction, written in the way it's supposed to work for a galvanic cell, which means this is a half reaction. Nickel metal goes to 0.752 molar nickel cations, and the 0.0343 molar gold ions are changing into gold metal. Well, that's a good thing. Let's get that gold back in metallic form. Okay. And now look, what's happening in the nickel metal that's making it +2, is it gaining or losing electrons? It went from 0 charge or 0 oxidation number to +2. It's going to lose 2 electrons. It's being oxidized. And ox, right? That's how you pair them up. And we got red and cat, meow. Is this being reduced? Yeah, it's gaining electrons to go from +3 to 0. Yes, okay. So we got the anode over here on the left with the nickel. We got the cathode over there. So I'm going to draw a galvanic cell. I know who's what, anode and cathode, show the direction. It's always this way. The anode is producing electrons, which then can flow from the anode to the cathode. Cathode's gobbling them up, right? The gold ions are like, feed us electrons so we can turn into metallic gold. So the electrons are going to be pulling it off the wires. Like, give me those electrons so we can be reduced. All right. When you draw it, I don't need a lot of detail, but you do need some. You need, if this says solid and it's a metal, then you definitely need a metal, like a, I don't know, square, rectangle or something. Label it. This is nickel. Put it in a beaker or a test tube, whatever you want, and then label some nickel +2 ions in there, because that's a second item. This line is telling you there's a phase change from solid to aqueous. And then the double line is a salt bridge. So that's usually, this U-shaped tube. And if you just draw it like that, I'll know what you mean, but you want to make sure you might write salt bridge. And then here's your second beaker. Make sure that the liquid goes over the bottom of the salt bridge so it actually completes a circuit. Stick in a different piece of metal, right? That's going to be the gold, Au. And there's some gold ions here. And I haven't got my battery, my galvanic cell connected yet. So get your wire here, connect the 2 electrodes together. And then it says show the direction of electron flow. So you have to say electron flow. goes this way. Oh, and label the anode. Okay, anode is here. It goes in alphabetical order. Anode to cathode. My handwriting is so bad. That's supposed to say electron flow. I think I'm good with part A. Yep, I got all my components. Good. Identifying the reducing agent. Remember opposite. The reducing agent, it is being oxidized. How is it reducing somebody else? Well, it's using its own electrons, saying, hey, I'm going to lose some electrons. I'm going to stick it in the pocket. I'm a secret agent. I'm going to slip it into the pocket without them knowing and reduce somebody else, hand off some electrons. Anyway, whatever works, right? That little image in my head with the guy with the trench coat and the hat sneak up beside someone and slipping some electrons in their pocket. Dun, 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 reducing agent. That works for me. But it's also helpful to identify it's the opposite. So if this thing is being a reducing agent, then it itself has to be oxidized. And at the anode, it's being oxidized. So it's the nickel metal that's losing electrons. So 6B, it's nickel metal. If you put nickel 2+, you're not gonna get full credit because it's a nickel metal that's losing the electrons to become nickel 2+. Nickel 2+ already lost electrons. It can't be the reducing agent. It was a nickel metal. Okay, what is the E for this cell? Wait, I thought to get that from the chart. No, that's the E0. So if you forget, go to the top of the exam, and there it is. Here's the E with no little superscript 0, the superscript, what is that, degree symbol? That means standard. That means, you know, everything's at standard potential, standard concentrations. So these voltages are when all your aqueous solutions are at 1 molar, the gases are 1 atmosphere. If you change those, the voltage will change, and you can calculate how it can change using the Nernst equation. Yeah, so you get the standard potential, subtract it from this, gosh, what is that constant called? Faraday constant? No, I can't remember that. Divided by the number of electrons times the log of the Q. Remember Q from equilibrium? The reaction quotient, it's products divided by reactants. So that's the equation we need to use now. Let me see if I can make sure. You don't have to have it memorized. Come on, pen. But for 6C, this is the equation we need. The actual cell potential or voltage is equal to the standard potential minus 0.5 something all over N times the log of the Q. Let's go back and get the rest of it. 0.0591. Yep, so I'm missing a 0. Okay. 0.591, right? Just check over here. So zipping back and forth on that handout. Yeah. There it is. Good. Okay. All right, so what do we know? We need to find this. So let's go after this one first. So go find nickel going to 2+, and then it'll be written backwards. Gold going to gold 3+. Screen is ticklish. That zoomed in unexpectedly. Okay, gold, where are you? See silver, there it is. Here's gold. So gold is a +1,5. Oh, and that's written the right order, right? The gold was being reduced. The nickel, however, oh, it's down here. That's where, hey, get out of the way. The nickel was being oxidized, so we need to reverse this. Instead of a negative 0.25, it's a positive 0.25. Okay, so E0 is a plus 150 for the gold. And then it turns out to be a plus for the, we want the nickel going to nickel 2 plus. So the standard voltage is it's a positive 1.75 volts. Okay, so we have that number, and then we need to find N. So in the balance equation, yeah, so thankfully this one's not too bad to balance. You need to find out, let's look at our, when we balanced number 1 or number 2, forget which one we did. This one, yeah, number 1. So right here, when we had to add our half reactions together, we had to change it to 12 electrons for zinc because the arsenic needed 12 electrons. So N would be 12 if we were talking about this redox reaction. So yeah, this could get hairy, but this one's not too bad. Let's balance the reaction. Well, what's our half reactions? It's nickel going to nickel 2 plus, and it's gold 3 plus going to gold metal. First thing, check and make sure your atoms are balanced. Yep, I got one of each redox active metal. Good. Balance your oxidation numbers. Okay, nickel has a 0 oxidation number. Nickel plus 2 is a plus 2 oxidation number. Need to balance that with a couple electrons. Do the same thing over here. Hey, the gold at the end has a 0 oxidation number, but start with a plus 3, so I need to add 3 electrons here. Cool. Okay, then balance the charge. Well, this side's 0 and that's 0, and this side's 0 and that's 0. Excellent. If the charge wasn't balanced, you had hydrogen ions or hydroxide ions. Didn't need to do that. If we had, we'd have to balance it with water. Don't have to do that here. Yeah, we got our half reactions are balanced. Now merge them together. I got 2 electrons and 3 electrons. Now I need them to cancel. You have to multiply all this by 3 to get 6 electrons. And then we have to multiply all this by 2 to get 6 electrons. N is equal to 6. That's as far as you had to go on balancing. We just need to find how many electrons are being exchanged. 6 of them. Okay, now we need the Q. Q is the products over the reactants. So maybe I should finish balancing this equation. Yes, we do need the balance equation for the Q. Okay, we multiply by 3, multiply by 2, so then our reactants are going to be 3 nickels, solid, plus, this is going to be 2, plus 3 golds, going to, I'm going to leave out the electrons because they cancel out. Product's going to be 3 nickel cations, aqueous, and electrons cancel, and over here it's just 2 gold metals. Cool. Oh, I should put brackets around these, remind myself it's concentration. Okay, so our products are nickel plus 2, bracket, and that 3. Yes, that's our exponent. That's really why we had to balance the equation. So we calculate the Q. And now, and then this is a solid, so it doesn't show up in our Q in the equilibrium constant. No. We're done with the products. Reactants, there's a solid, leave it out. Put in the aqueous or the gases. There's an aqueous, so it shows up Au3 plus with the exponent of 2. Cool. We need a number though. The nickel concentration is 0.752. Wow. 0.752 cubed divided by the gold concentration is a 0.0343 squared. And I'm looking over here at my notes. But you put that in your calculator and I got 361. I don't know if I carried enough significant figures, but let's just run with it. I will not be nitpicky on sig figs for the test. Okay. The whole thing had to go in the Nernst equation. I think I got all my pieces. Let's merge them all together. So I'm going to begin by rewriting the Nernst equation. The actual cell potential is equal to the standard potential, which is 1.75, minus 0.0591 divided by n is 6 electrons, times the log of the Q, which we found to be 361. Nice. Okay, now we just need to grab the calculator. Be careful to take the log first, then multiply by 0.0591, divide by 6, change the sign. And I discovered it doesn't change it very much. It starts at 1.75 and it ends up at 1.72 volts positive. There we go. That's 6C. We found the we found the cell potential. Cool. Let's jump down to number 14 because it dealt with the same cell. So I know I'm taking these out of orders, but they're connected. So number 14 says, hey, consider that galvanic cell we worked out in number 6. Same exact cell, galvanic cell. Which one of the following changes to the cell would cause the cell potential to increase, become more positive? Okay, so what it's saying is we want this number to get bigger, and we saw it got smaller. So we don't want that. So you're subtracting this. So to get this thing to add, we need this whole thing to change its sign to be plus, which means you need to take a log of a number that's smaller than 1. So what is this number? It's the Q. And we want something smaller than 1. Well, that means you need this one to be large and this to be small. Okay, that's how you solve number 14 from a math point of view. You can do it from a chemical point of view too. You can say, well, why don't we just use Le Chatelier's principle? We want the cell potential to increase. Or in other words, these cells, I think of them as batteries. So you want a stronger battery. You want a fresh battery. So you want all reactants and no products, right? So when a cell goes dead, the reactants have spent, they all become products. There's no more reaction, no more cell potential. Yeah, it's a dead battery. This principle says, okay, to get the reaction to work, make sure your reactants are in high concentration and the products are in low. So we want lots of reactants. Well, that's exactly what the Q was trying to tell us. If you have lots of reactants, then your denominator is large. So you get the same answer, which one's a lot of reactants? Or reactants are the nickel plus. So we want to increase the concentration of nickel plus. If it said decrease here, that would also be correct, right? If you reduce, did I do this right? Nickel. Oh, I'm looking at this equation, sorry, got confused. Yeah, this is your reactant. So I did not do it right. Where's my reverse button? Gosh, almost have to re-record this whole video for a stupid mistake, but I got it. Okay, let's start that again. Gold is the reactant. You need lots of gold. Yes, this is the reactant. Okay, so increase the concentration of gold. Right? Let's go to the answer key and look up number 14, double check. Yes. Okay, so at least agree with the answer key. But that makes sense. Now, as I look at the balance equation, find my reactants. Oh, and the point is, you can also make Q We want more negative. So that when you want the Q to be negative, the log of the Q to be negative rather. So when you multiply it by negative, it turns out to be positive. So you can reduce the products too. And the products are in a nickel. So if it said decrease the concentration of nickel, that would also then become a correct answer. I'll try not to give you two correct answers. But anyways, just saying, maybe the question might say, hey, decrease the concentration of nickel and decrease the concentration of gold. Well, in that case, the answer is decrease the concentration of nickel. Lower the products. So effectively, more reactants want to drive the reaction forward. Okay, hopefully I didn't mess that up too badly. That was 14, but we went out of order. Any more down here? Yes, going back, we had 6, then 14. Let's go back to 7. 7, we're changing units now. Instead of talking about electrochemistry, let's switch over to transition metals. Take a little sip of tea too. I'm drinking peppermint tea. I don't know, my brain goes different places. In the compound, that thing, the complex ion is octahedral. 7A, what's the charge on cobalt, the CO? Okay. Actually, what I'm going to do is jump down here to answer 7D first. What's the counterion? The counterions are things not inside the brackets. It means that whatever's outside the bracket is ionic. It's being held by an ionic bond. So this K must be a plus. That's a counterion. And then the other thing inside brackets is the transition metal complex. Think of it as just a big, large ion. It's all covalently held together. Even though you have some things like oxalate, which is ionic, but transition metals are weird. This ionic molecule, oxalate, is being covalently bound to the cobalt. Okay. So to get at the charge of cobalt, you have to peel away at this molecule, this salt, really. So I pulled away the counterion, K+, now left with the anion, right? Because K+ is positive. So the transition metal complex must be ionic. To balance this charge, oh, there's only one K, so there's only one plus. Now we know that the transition metal complex is a -1. Okay. Now start peeling, we still need to find the cobalt. So peel away now the ligands. The ligands are the oxalate ion, ions plural, there's 2 of them. And the water molecule, I know there's 2 of them, but you only have to list the identities. There's oxalates here and there's water here. Yeah, there's 2 of each. Got 7E done. Still trying to do 7A. If you forget the charge, no problem. Go to the top of the list and look it up. So I was pretty generous with that. So here's oxalate -2. Everybody else is negative. Hey, carbonyl, do you have a charge? Nope, you don't. Ammonia doesn't. The ene doesn't. So that's kind of cool. So go up here. That's handy in case you forget the charges. Okay, so peeling away still the cobalt and 2 oxalates, each with a -2 charge, and 2 waters make up this whole complex with a net charge of -1. Cobalt, we're trying to get your charge, and the oxalate has a total of a -4, right? There's 2 of them at -2 each. Water doesn't have any charge. So all of these things, the cobalt, these 2 things have charge, has to net add up to a net charge of -1. So X is a +3, right? X -4 equals -1, add 4 to both sides. Yep, X equals +3. What's the oxidation number of cobalt? Not a trick question. It's still +3. Yeah, so I got the charge, which is actually, since cobalt's just a monatomic ion, the charge is defined to be the oxidation number by our It's oxidation number rules. I forget, when we had to calculate oxidation numbers, that was one of the guidelines. 7C, what's the coordination number of cobalt? Okay, so go back to your ligands. This is something you have to remember. You have to remember how many times they bite or they bond. So these are all the ligands that I could choose from. Everybody's monodentate, meaning dentate, remember dentures, teeth, mono teeth. It's like one bite, one tooth. Most of these are monodentate. They bind one time, except for the oxalate. Anybody else a -2? That's not why it binds twice, but that's a good way of remembering it. Of the ones I gave you, it's the only one that's a -2. So it binds twice, bidentate. It's got 2 teeth. If you draw out the Lewis dot structure of oxalate, it looks like this. It turns out both oxygens can then attach to a covalent bond to a metal, make a bond and another bond. One oxalate molecule ion can bond twice, bidentate. The ene can do the same thing. Ene has ethylene diamine. So maybe there's a clue. There's a 2 here, and there's a di here to remind you, those are the only 2. Double check. Yeah. Those are the only 2 that bind twice. They're bidentate. Ethylene diamine and oxalate. Oh, you want to see ethylene diamine? I heard someone say it. Well, in my head. Nitrogen and diamine. Diamine 2, where's the other one here? Nitrogen has a lone pair, and it uses that lone pair to make a coordinate covalent bond to your metal. So it loses the lone pair and gets a covalent bond in this place 2 times. Bidentate. Okay. Coordination number. Okay, so bidentate, making 2 bonds. Everybody else is monodentate. Dentate, I think that's how you spell it. So there's 2 waters for 2 bonds. There's 2 oxalate, each one's 2 bonds. So this one's going to make 4 bonds. The oxalate, both oxalates total up to 4 bonds to the cobalt. Water totals up to 2 more to give you 6. It's a coordination number of 6. If you like pictures, let's see. It's octahedral. So our bonds are going to be, there's an up-down bond, and then 4 in a square, 2 bonds going away from us, 2 bonds coming out towards us. Those are wedge bonds. And then, I don't know, let's make the oxalate here. Oh, we haven't seen skeletal drawings yet, sorry. So drawing my C's. There's an oxalate, I'll put another one here. And then the water can go here and it attaches by the oxygen. So I know it looks weird, putting the H's afterwards, but there you go. Coordination number 6. Actually, maybe if you just looked at octahedral and knew this, that would have told you 6. Didn't see that till right now. That would have worked. Okay, 7F. Draw the d orbital splitting diagram for cobalt with a low spin case, or draw a d orbital splitting diagram for cobalt high spin case. So in the homework and other places in the sample test, we talked about how you could look at the ligands and predict whether it was a high spin or low spin. We said that at water and below, it's probably weak field ligands, and oxalate and water are weak field, which means they don't, the 2 energy levels don't split very far, which gives you lots of spin. This is the high spin case. Now, I want on this question for you to draw both possibilities. So if it asks, and if you see the question, it wants both, then give me both. even though you could argue, wait, Dennis, based on the ligands, it should only be the high spin case. But I want to know if you can draw both. That's what I'm looking for. So just humor me. It's asking for a low spin case. So low spin, lots of pairing. So low spin. And this one has lots of unpaired electrons. So high spin. That's how I get these terms straight, because you got your strong field and your weak field, but the strong field produces low spin. Everything's opposite in chemistry. So low spin, lots of pairing. That means you have 3 down low and 2 up high. So when the gap is due to a strong, that's supposed to be a bracket. If you have a strong field, then you get a big separation, so that after nature puts in these electrons, oh, I don't know how many electrons there are. Should go count them. After she puts in electrons, then she has to decide, should I put an electron way up here or I just pair up? And it's a little bit of energy, takes a little bit of energy to pair up, but that's much better than going way up here, which means you're pairing up, not having a lot of unpaired electrons. When you have high spin, that's when you can put electrons here, and then after you put 3 in there, the 4th one, should we pair up or put up here? Turns out it's less energy to put one up here because it's a small gap. This is a weak field splitting. Okay, let's find out how many electrons are supposed to be in here. I'm guessing at least 2, or maybe I have to get the eraser out. Let's find out. Cobalt, where are you on the periodic table? I have it up here somewhere on the right. Cobalt, cobalt, cobalt. You're element 27, which means you have 7 d electrons. Your noble gas configuration is that of argon plus the 4s2s, and then let's figure out the 3ds. But the key is there's 7 d electrons. Okay, so cobalt has the electron configuration of argon and the 4s2, and then there's 3 d. Well, that's, sorry, I don't know why I'm doing that. 7? 7. That's right. I'm trying to think of the 2 exceptions. That's chromium. That's why I'm getting messed up. It's chromium and copper, 2 C's. Those have exceptions. Anyways, if we don't get the exception here, this is cobalt. So maybe we'll see the exception in another problem. Okay, we're good. 7 d electrons. No, that's for the neutral atom. What's the actual charge? It's a +3. I'm glad I remembered that. It's +3. So you always lose the highest occupied orbitals. So the highest shell loses electrons first because they're closest to escaping. They're farthest from the nucleus, so they come out first. But it's supposed to be +3, so I have to lose one of these. So now you have 6 d electrons in the copper cobalt, the cobalt +3. Okay, 6 electrons. So if it's weak field, 1, 2, 3, electron number 4 of 6 goes here, then goes 5, and then 6 comes down here and pairs up. But if it's a strong field, then the 6 electrons, 3 of them goes here, and 3rd one says, whoa, that's too much work, let's just pair up. 4, 5, 6, and there's no unpaired electrons. There's 4 here. And there's no unpaired electrons. You know what? I know the question doesn't ask for it, but there are other exam questions and sample test questions that would ask for diamagnetic and paramagnetic. Which one is the strong field? That's diamagnetic. There are no unpaired electrons. If you have even one unpaired electron, that makes the metal paramagnetic. If everybody's paired up, diamagnetic. I think we got them all. 7 had a lot of parts, but we got through them all. Cool. Up and over. 10, more about transition metals. Solution A contains that compound lithium, niobium, chloride, whatever. Solution B contains a compound also with NB, but it's got ene, ethylene diamine in there, and hydroxide as the counterion. One of the solutions absorbs light at 420 nanometers. The other solution absorbs that light at 530 nanometers. Which solution, A or B? Okay, A, this one's A, and this one is B. Absorbs light at 420. Okay, so what's the difference between 420 and 530? These are wavelengths. So if you don't know off the top of your head, see if there's any help on the this thingy. Top of the exam will have your equations, and I don't, there it is. There's lambda right there. Lambda nu equals C. And also E equals H nu. Grab those, grab both of those. Lambda nu equals C and E equals H nu. Okay, so what you need to know, the minimum, is that this is frequency. H is Planck's constant. Guess you don't have to know that. More importantly, if nu, the frequency, is a big number, multiplying this will give you a big number, big energy. If frequency is small, then the energy will be small. So energy is proportional to the frequency. And I always think about just moving my hand to vibrate back and forth. And this is low frequency. That's pretty easy, low energy. And this is high energy, and my hand's going to get tired because it takes so much energy to move it that fast. High frequency, high energy. And then over here, things are opposite. C is a constant. Sure, you can go look it up. But if this goes up, then this one has to come down. So that when you multiply them together, it still equals the same number. So these are inversely proportional to each other. You can divide it, get lambda over here, so you can see that it's inversely proportional. Okay, so if you want a high frequency, then your lambda is going to be small. So let's go with that. Which one has a higher energy, 420 or 530? The smaller wavelength. This one has high energy. Higher E, higher frequency. I mean, the lambda is bigger. So if you make lambda big, then the frequency has to come down. And that means the energy comes down. Okay, but we said the 420 is a higher energy. So when we're talking about complexes, transition metal complexes, so it's a difference between the weak, like electron going boop right here with the weak field, or is it a strong field? You got the electron goes, whoa, go way up there, absorb a lot of light in the strong field. You need a lot of energy to jump this. That takes high energy. Okay, so the 420 is going to be the higher energy with the strong field. There we go, that's what we needed. So which one of these ligands is strong field? They're both NB, so that's nice. It's nice to have the metal be the same. We have chloride, and then what do we compare it to, hydroxide or ene? Well, hydroxide is a counterion. It's not in the brackets. Don't look at that one. That's an ionically bound thing. It's not a ligand. The ligand is going to determine strong or weak field. So the ene is within the brackets. So compare the ene to the chloride. Scroll over, and we got the ene, who is right here. It's above higher than water. That's a strong field. Chloride, yep, it's after water. It's a weak field. So the ene is the strong field ligand. That's going to give us the high energy. Strong field ligand gives us high energy. So B, solution B should absorb light at 420. Because the other complex with the weak field should absorb weaker amounts of energy, which is a higher wavelength. Good. 10 is done. 16, jumping ahead. So the other ones, we did 14. The other ones are kind of minor. Well, I shouldn't say that. They might be important, but I think the answer key is pretty straightforward. I'm doing the more complicated ones. So definitely go back and at least look at all the problems. So you're ready for the exam. Okay, 16, what's the name of this complex? Okay, I put a tough one on the sample test. I won't give you two complexes, the name, because that's what's happening here. You got two sets of brackets. So this thing here is one transition metal complex, and this is a second one. There's a cation. They usually list cations, and then the anion second. Okay, so you have to name both of them in this problem on the exam. There'll just be one. Okay, so what are we going to do? Well, I guess I just jump right in. We need to, what's the base of a name? Well, you put the ligands first in alphabetical order. So alpha order ligands. And then you add the metal. And then remember to add 8 if it's negative. If the complex is negative, not the metal ion. The metal could have a plus charge on it, but the whole complex is negative, then you have to add the 8 suffix. And then you need the Roman numeral for the charge of that metal ion. Yep, that's the format, if you will, for naming these. Okay, so CO, let's just do the first one, CO. I'm going to cheat. It's not cheating. I'm giving you these. CO is right here. First one in the series is carbonyl. That's the name of it. You'll need to know what the prefix is. Sorry, going too far. You need to know a prefix for how many carbonyls do I have? I have 6 of them. That's hexagon, like honeycomb, 6 sides. So hexacarbonyl. And then it's nickel. And there's this thing. No, this thing is, the first thing is going to be the cation. The second one's going to be the anion. The second one needs the 8 ending. So I just need the charge. Ooh. Ooh. Huh. Okay. So we need to break this down. I want to know what the charge on the brackets is. And it doesn't tell me. It's saying, well, no, this whole thing is balancing out to a neutral complex. So there's a couple ways to analyze this. One is to look at that 3 and then just go crazy writing everything out. So this subscript 3 right there says you have 3 nickel complexes. That's supposed to be a C. And then this 2 subscript, you have 2 chromium complexes with the oxalate there. And guess what? The whole thing adds up to 0 charge. This is a neutral compound, cation with anion. Nature says, yep, you're good. You balance your charges. Well, what can these charges be? Well, process of elimination or just trial and error. Well, if this is +1 and that's -1. No, this adds up to each one being a +1 will give you a total of +3, and that's a -2. Well, what if this one's a 2 and that one's a 3? Yeah, that's the way to do it. You can make an educated guess. Crisscross this 3 and that 2. What is that like? That's like calcium and nitrogen. So the charge is +2 and -3, but you crisscross to get the chemical formula? Yeah, this is a neutral compound. It's got a total of 3 times 2 plus, which is a 6 plus. All the calciums have the 6 plus. And then you have 2 times a -3 on -6. Two nitrogens that are both -3 gives you a -6. So this makes a neutral complex. Well, that's what we got here. There's a 3 and a 2 as subscript. So crisscross them. Put the 2 there and the 3 there. And that will work. If these are all +2 and this is a -3, all the charges balance out. Cool. Okay. Then if one nickel complex, the whole brackets, is a +2, go and take a look at the carbonyl group. It's 0 charge. Right, so right here, CO, no charge on that carbonyl, carbon monoxide. So in order for this nickel carbonyl group to have any charge, it all has to belong to nickel because CO is neutral. And we said it's a +2 and whole thing. So the nickel is a +2. Cool, we got half of it named. The other side, well, alphabetical order on the ligands. Those are oxalate, C2O4. You can go back and look at the top of the sample test. And how many oxalates do I have? I have 3 of them. So tricycles have 3 wheels. So triangles have 3 sides. And it's oxalate. Oxalato is what it is. Again, you didn't have to memorize that. But if you work on these long enough, some things they just start sticking in your head. Yeah, oxalato. And there's a -2 charge on it. Oops, too far. Okay, so there's 3 oxalates, and then we put in chromium, and we know it's an anion, so instead of writing chromium, we're going to put chromate. You have to add the 8 ending. There it is, 8 ending if it's a negative, and this is a -3 complex. And then finally, what's the charge on the chromate? Well, there's 3 oxalate. Here, let's put down here. Minus. 3 minus. Okay. Chromium, we want to find out what your charge is. There's 3 oxalate, and each oxalate, remember I pointed out, is a -2. And you know that from polyatomic ions, oxalate has a -2 charge. And that all has to equal a -3 net charge. So x minus 6 equals -3. Add 6 to both sides, and x is a +3. Yay, so that's the whole, that's a pretty complicated looking salt. But yeah, just kind of, this is good enough. It's hexacarbonyl carbonyl 2, trioxalato chromate 3. Done. Thank goodness. That was tough. Ooh, drawing. This shouldn't be so bad, right? Draw and label cis and trans isomers. Okay, so remember cis, put an S in there. It's a soft C. You can write it SIS, which reminds me they need to have groups on the same side. Transcontinental, they're 180 degrees across. Okay, what are? We're talking about 2 things, so what specifically? Well, in platinum, there's 4 of these nitro groups, 1 fluorine and 1 hydroxide. So there's a whole bunch of very similar things, but there's 2 things that are different. Okay, so that's the 2 things that we want to put totally across. So put maybe the fluorine up here and the hydroxide down here. Now they're across. This one's a trans. If you don't want to do it across that way, you could say, well, I'm going to put one back, one forward. They're totally across, or any other form you want. It's going to be trans. You get partial credit for this. That's not the full complex. We need to draw the whole darn thing. There's 4 nitro groups, so I need 4 more bonds. NO2, 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 NO2. Do the same thing here. NO2, 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 NO2. And of course, you only have to draw one. I'm just saying there's more than one answer. Okay, what about the cis one? Well, make them together on the same side. So like the fluorine and the nitro, these specific groups are together. They're like 90 degrees. How about that? 90 degrees apart. That'll make them side by side. So you can put these 2 nitro groups. You could say, hey, they're cis to each other. So put the fluorine and the hydroxyl group here, or down here, or just here, or there, anything that's 90 degrees apart. So I don't know. How about we keep the fluorine up there and we put the hydroxide here? That's one option. They're 90 degrees apart. Then to get full credit, finish drawing the rest of the complex. That's supposed to be a wedge. Good. Got 4 nitros, a fluorine, and hydroxide. We're done. Yay, that was pretty nice. 19. Ooh, is that the last one? It is. Okay, what color would you expect for each of these complexes? Most of the time you just look and see if it's a high field, sorry, a strong field or a weak field ligand. But there's one exception, and that's if you got the entire d orbitals full. So how do you get color? I think I drew something already. Let's just go point at that. Yeah, it's right here. The way you get color is you have to have electrons in the lower orbital, and there has to be room up high for the electron so that the electron can absorb light, give it enough energy to jump into that higher orbital. And the light has to have exactly the same amount of energy as this energy difference between where the electron begins and where it ends. So if you have a metal complex, doesn't matter if it's strong or weak, and there's electrons up here, there's no room. So you'll have electrons down here, but they can't jump up. There's no room. Each orbital can only hold 2 electrons. You're going to get no absorption, which means there's no color. Light will just go through it. A solution of the transition metal complex where the upper orbitals of your d splitting pattern, it's all full. There's no room for the electron to jump up there. The light will just go through. It won't be absorbed. Okay, so that's the one thing you have to look out for. So to make sure you don't get tripped on it, let's find out how many electrons are in the d orbital. Well, let's peel it away. I got my bracket here and here. So that's a counterion. There's 2 of them, which means my complex, whoops, there's no bracket, parentheses there. It's over here. My bracket must be a -2 complex. And then peel away the chromium. Charge on the chromium plus 3 of these negatively charged chlorines. Water is neutral, has to add up to -2. So X, that's a +2. This is a +1, right? Dennis, come on. I should take a break. But it's the last problem. I can do this. Start all over, add 3. Yes, it's a +1. Okay, so chromium is a +1. It loses 1 electron from where it normally starts. So where does it start? Well, go to the periodic table. That's how all the first row of transition metals begins. Chromium, where are you? Chromium, your element 24. You have 4d electrons, or do you? Yeah, chromium and copper are the exceptions. Chromium, you should have 4 electrons if you follow the trend. Should be 4s2, d4. But that's not right. This is one of the exceptions. So if you have your 4s electrons, and then you have your 3d, there's supposed to be 4 here. Well, it turns out for chromium, what it does is one of these electrons moves over. And now this gives the element a little more stability. Something about having the d orbitals half filled makes it more stable. So even though it takes a little bit of energy to move, that's another arrow, move this, the electron was here, give it a little more oomph, but overall, it's much more stabilizing. It kind of lowers in energy. You just have to remember that. So the ground state for chromium is 4s1, 3d5. And then chromium, that's for chromium metal, and that's 0 oxidation state. A chromium +1, which is what we just found out, you lose 1 electron from the highest orbital. So it's a 3d5. Oh, and then now we know the d orbitals won't be filled. It will absorb color. We just have to decide, is this a strong field or a weak field? So this is weak. This is strong. It doesn't matter. Both will absorb light. We just have to figure out, well, which one is it? So inside our brackets, we have water and chloride. So are they strong field or weak field? Chloride and water. Chloride is here, way to the right. Water is the break point. Water is a weak field. Everybody else is also weak field to the right. Weak field. We have this situation here. Let's get the whole thing in there. Okay, so the ligands, chloride and water, they give us the weak field splitting, which means this is small. Is that high energy or low? It's low energy. It's a small energy, small gap. So E, H nu, so that means this is a low frequency, which means the wavelength should be high or long. And so now it wants color. So what you need to remember is that white light, at least our perception of light with our human eyes, whenever we see all the primary colors, red, yellow, blue, our eyes say, hey, it's just white light. We're getting all 3 in here. Red has the longest wavelength. Blue is the shortest. And red is the lowest frequency of the visible spectrum, and blue is the highest frequency. How do you remember that? Well, after blue is ultraviolet and ouch sunburns, lots of energy, burning your skin. So high energy. And then it's opposite. Cool. And then, okay, so then we're going to get the weak field. So red light is going to be absorbed. And if it's being absorbed, what light is coming out? Just the blue and the yellow. And did you remember that blue and yellow make green? Yeah, you get a green solution. So what color? This we expect to be a green color. Cool. All righty. That's all for now. Good luck on the exam.